Dear students, now let us see whether the spring force is conservative force or non-conservative force. Fx is conservative if it can be expressed as dx. Now let us see, it's the potential energy of a spring. Already we derived expression for potential energy of a spring and we got the expression as of kx square. Differentiating this with respect to x, we get 1 by 2 k into x square. When differentiated, we get 2x. 2 gets cancelled. So multiplying on both sides by minus 1, minus kx is equal to minus dv by dx. But by Hooke's law, spring force is defined as minus kx. Therefore, on left hand side you can write Fs is equal to minus dv by dx. See, the spring force is expressible in the form minus dv by dx. Therefore Fs is conservative. Now state and prove law of conservation of mechanical energy in case of a freely falling body. A body is dropped from here. We are choosing three different positions at A, B and C. At the three different positions, if the total mechanical energy is same, then we can say the law of conservation of mechanical energy is proved. So according to the statement, what is the statement of law of conservation of mechanical energy? If the forces are conservative, total mechanical energy at A is equal to total mechanical energy at B is equal to total mechanical energy at C. Proof. Total mechanical energy is nothing but sum of potential energy and kinetic energy. Now let us select at position A. At position A, potential energy is mg. That A position is at a height of capital H from ground, and kinetic energy of m VA square, but here you are dropping the body, therefore half m z. Now total energy is VA plus KA is equal to mgh plus 0 is equal to mgh. So now let us go for second position, and that is at position B. At position B, VB is equal to mgh, height is h, and kinetic energy half m VB square. See here, its velocity is VB. Now the object has moved from A to B. The object has displaced downward from A to B, and the displacement is see, let us write first initial velocity. The object has displaced downward from A to B. Initial velocity 0. Final velocity is VB, and distance or displacement, and displacement is from A to B. The displacement is capital H minus H, but the displacement is downward, therefore we put minus sign here. For upward displacement positive, for downward displacement negative. Because displacement is downward. Now according to kinematic equation, V square minus C square is equal to 2AS. VB square 0 square is equal to, and here A, in place of A we write minus G. And here A is equal to minus G. Why A is equal to minus G? This is also downward. Minus sign, because G is downward. Whether, say, if this is Earth, this is an object, whether it is moving upward or downward. Gravitational force on it is always downward. Therefore, acceleration also downward. Therefore, minus sign comes. Here displacement is downward, therefore minus of minus into minus plus. Let us substitute this in kinetic energy. Half mvb square, half m into 2g, h minus h, 2 gets cancelled. Now total energy, potential energy plus kinetic energy. Potential energy is mgh and kinetic energy is mgh minus h. Plus mgh minus mgh cancels, so you get mg capital H. Now third, when the object is at position C. When the object is at position C. With vc velocity, the object reaches the ground. Therefore, vc is equal to potential energy is, see, it is almost touching the ground, therefore it is 0. kc half m vc square. The object has displaced downward from A to C. Displaced from A to C. Now, initial velocity at A 0, final velocity at C is Vc. A is always minus G, because Earth gravitational force is always downward. Now displacement is also downward from A to C. From A to C the displacement is h, but here we write minus h because the displacement is downward. Because of downward displacement. Now, third kinematic equation. V square minus C square is 2as, Vc square minus 0 square 2 into minus G minus H, that is equal to 2GH. So substituting this value in the Kc, half mvc squared, half m into 2gh mgh. Now total energy Vc plus Kc, 0 plus now when the object was at position A, the total energy is mg capital H. When the object was at position B, then the total energy, total mechanical energy, also same mg capital H. And when the object is at position C, there also the total mechanical energy is mg capital H. From equations 1, 2 and 3, from equations 1, 2 and 3, what we got? EA is equal to EV is equal to EC. Total mechanical energy is same. Therefore, law of conservation of energy is proved. Now let us consider solved example 6.7. A bob of mass m is suspended by a light string of length L. It is imparted a horizontal velocity Vo at the lowest point S such that it completes a semicircular trajectory in the vertical plane with the string becoming slack only on reaching the topmost point. C. This is shown in figure 6.6. Obtain an expression for Vo, the speeds at points B and C. Third, the ratio of the kinetic energy is Kb by Kc at B and C. Comment on the nature of the trajectory of the bob after it reaches the point C. So here, solved example 6.7. Here a bob of mass m, its mass is m, and on that the gravitational force will be mg. Since the gravitational force tries to pull the string, tries to stretch the string, a restoring force is developed inside the string opposing the stretching, and that is tension in the string. Say this is TA. This position is A, suppose. This position is A. Here with some initial velocity, with initial horizontal velocity, you push the bob so that it completes one circle like this. The length of the string is L. So this L itself becomes radius of the circle. Here its velocity is V. See, this position is B. This position is C. Here the velocity is Vb and here the velocity is Vc. Here the tension in the string is Tc, that is 0. Y0 means here it is given. Here it is given here. But with string becoming slack only on reaching the topmost point. It is becoming slack means tension in the string is 0. And here the gravitational force is mg. Similarly here, when the bob is here, tension in the string is Tb. This is the center of the circle. This is O. Now this is the lowest point for the bob. So this can be taken as zero potential energy level. At this point, potential energy of the bob is 0. As it moves up, height is increasing, therefore potential energy increases and kinetic energy decreases. From here to here, height is decreasing, therefore potential energy decreases, kinetic energy increases. Now we will be making use of law of conservation of mechanical energy to solve the problem. At position A, potential energy is 0. Kinetic energy is half m v naught square, and total energy is equal to potential energy plus kinetic energy, 0 plus half mv naught square. Now centripetal force. What is centripetal force? Centripetal force is force towards center of the circle. Force towards center of the circle. See, at position A, force towards center of the circle is TA and away from center is mg. So it becomes towards is taken as positive and away is taken as negative. But centripetal force formula is mv square by r. M Here velocity is v naught square by r. R means radius of the circle. Radius of the circle is L. Now let us go for next position. At position B. At position B, potential energy at B, see it is at a height of L. Therefore mgl, potential energy. Kinetic energy is half m v square. Total energy, potential energy plus kinetic energy. mgl plus half m v square. At position C, potential energy at C, it is at here the bob is at a height of here to here L, here to here L. L plus L, 2L. So mg 2L. Kinetic energy half m v square. Total energy is plus half m v square. Now centripetal force is nothing but force towards center of circle. So at position C, centripetal force mv square by r, or mvc square by L. And here force towards center of the circle is, one force is mg and another force is Tc. So Tc plus mg. But when the object is at C, tension in the string is 0. Or mvc square is equal to mgl. M gets cancelled, or Vc is equal to GL under root. This is one answer. Now say this is fifth equation. Substituting fifth equation in fourth equation gives, where is the fourth equation here? In place of MVC square you can write MGL. EC is equal to 2mgl plus half into MVC square. MVC square is equal to mgl. So taking mgl common, here 2, here 1 by 2. 2 to the 4 plus 1, 5 by 2. 5 by 2 mgl. This is equal to 5 by 2 mgl. This is sixth equation. By law of conservation of total mechanical energy, EA is equal to EC. We have chosen three different positions, and at all the three positions total mechanical energy will be same. If you choose A and C positions, total energy at A is equal to total energy at C. What is the total energy at A? Total energy at A from equation 1 is half m V naught square, and total energy EC is 5 by 2 mgl. M gets cancelled, 2 gets cancelled. From this you have VO is equal to 5gl under root. So this is another answer. By law of conservation of energy, EB is equal to EC. Total energy at B, according to third equation, the third equation it is available, mgl plus half mvb square, and EC is 5 by 2 mgl. From this half mvb square is equal to 5 by 2 mgl minus, take this to right hand side, mgl. mgl can be taken common, so here 5 by 2 remains, here 1 remains. That is equal to 5 by 2 minus 1 means 5 minus 2, 3 by 2 mgl. Let me write this here. Let me write this here. half m vb square is equal to 3/2 mgl. m gets cancelled, 2 gets cancelled. vb is equal to 3 mgl under root. This is another answer. Now ratio between kinetic energy at B by kinetic energy at C is also asked. Kinetic energy at B is half m vb square. Kinetic energy at C position is half m vc square. Half m gets cancelled. Here vc square value vc square is equal to gl. Here vb square is equal to 3gl. So we got the ratio and is equal to 3, and this is another answer. So in this way we have completed this problem. Now the data from the solved example 6.8 is noted here. Mass of the car is 1000 kg. Its initial speed is 18 kilometers per hour. It is converted into meter per second. Spring constant. Spring constant is this much. Maximum compression in the spring, that is asked here. So actually here what is happening? This car is initially moving with this speed, goes and collides with the spring, so that the spring is compressed. Initially it is having some velocity, therefore it is having some kinetic energy. With some kinetic energy it pushes the spring and comes to rest. Here all the kinetic energy is converted into potential energy in the spring. So now let us write here. At maximum, see the spring is compressed to maximum extent. So at maximum compression, the KEF car is converted entirely into PE of spring. KEF car is half m VI square. PE of spring is 1/2 K XM square. 1/2 gets cancelled. So here XM square is equal to m by K into VI square, or XM is equal to m by K under root into VI. Mass of the car is 1000 kg. K value spring constant is 6250. VI initial speed is 5 meter per second. So substituting the values we get 2 meters. So the spring is compressed by 2 meters. So this is the answer. Now let us go for the solved example 6.9. This is just a continuation of this. Here the car is moving on smooth surface, that is frictional force is 0. But here the car is moving on rough surface, frictional force is not 0. With some initial velocity it is moving and colliding the spring. So when the compressed spring is exerting spring force to right hand side, so the spring is compressed from x is equal to 0 to x is equal to minus xm. So it is compressed maximum by this amount xm. So here now how many forces are working on the car? Let us take a free body diagram of the car. If this is our free body diagram of the car, see this side spring force is working. Here this is moving to right hand side, this is moving to left hand side, therefore the frictional force will be to right hand side. This is gravitational force and this is normal reaction. So these four forces are working on the car. See Fk is equal to mu k n, but n is equal to mg. So in this way frictional force is calculated, and similarly okay, now let us make use of, let us apply work energy theorem. According to work energy theorem, by work energy theorem, work done is equal to change in potential, change in kinetic energy. By work energy theorem, work done is equal to change in kinetic energy. So here partly work is done by spring force and partly work is done by frictional force. So here work is done by spring force plus and work is done by frictional force is equal to final kinetic energy minus initial kinetic energy. See, this is the equation 1. Now work done by spring force is stored as potential energy. Therefore Ws is equal to V is equal to 1 by 2 kxm square. Similarly, work done by frictional force is equal to frictional force dot displacement. So here frictional force is mu kmg dot displacement is xm. Let us write this afterwards. Now Wf is equal to Fk d. See, both are oppositely directed here.